So in our basic lesson we explored the difference between a secant and a tangent line. So the slope of the secant line is basically our normal average rate of change formula. And that's just finding the change in y over the change in x. And for this to work, you have to make sure you have 2 points. We found that when we tried to use the same point to find that rate of change at an instant, that it gave us the indeterminate form of 0 over 0. So that brings us to the slope of a tangent line. And we found that this was able to give us that instantaneous rate of change. But in order to do that, we had to use a limit. And what we were finding the limit of was the limit as h approaches 0 of the function f of a plus h minus f of a all over h. And using this limit allows us to only have to know 1 point in order to find an instantaneous rate of change. Okay, and so a quick visual to help kind of put those back together. So let's say we have some curve and we have some x value that would give us a y value of f of x. And since we can't just find the slope at a single point, we're going to have to kind of use a limit to get around that. Because like I said, when we used this average rate of change, we were getting a hole at the point itself because it was giving us indeterminate form. So instead we said, well, what if we pick a point that's just really close? Okay, now for illustrative purposes, I'm going to put it further away because I'm not a very good illustrator. But we're going to put it some distance away of h. So there's kind of like this distance of h that we've gone to. And so we can write that as x plus h as our new x value, which means that our new y value to go with that would also be f of x plus h. Okay, and our goal here, I kind of like to have like a slope triangle there. Our goal here is that as we find the limit, we're finding the limit as h is getting smaller, or the difference in the 2 points. So our point would get it closer and closer and closer and closer and closer, ideally until it was actually at the point, and then we would be able to find the limit there of the value that should actually be there if that hole were not. And that allows us to find that instantaneous rate of change at 1 point. Okay, so we're basically going to have the same setup for the official definition of the derivative. The only difference is that we're going to actually treat the derivative as a function we derive from f. And also we're going to use x's instead of a's. So the derivative of a function f with respect to the variable x is the function f prime, which we kind of notate with this little apostrophe mark, whose value at x can be expressed as f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And of course this is provided that the limit exists. And we'll go into that detail a little bit further down the road. But of course, yes, that means we'll be checking if limits exist or not, even in Unit 2. And so anywhere that the derivative exists, we are able to say that the function is differentiable. So derivative is a noun, differentiable is an adjective, and then of course we have the verb differentiate. So maybe just jot down a quick note that if you see something that asks you to find the derivative or something that asks you to differentiate, that's really asking you to do the same thing, which is to find that limit. Whoop, let's try that again. And again, just to reiterate, when we find the limit as h approaches 0 of the difference quotient, that means that we're finding the slope of the function at a specific x value. And now we're just going to do a few quick bullets of kind of like the different ways the derivative can be used. So the derivative allows us to describe how the curve is changing. It gives us that instantaneous rate of change. And I'm just going to abbreviate rate of change. And then it also gives us the slope of the tangent line. So anytime you see these phrases, it's basically asking you to find the derivative. Okay, so now let's do some notation. So there's really three main people who contributed to the notation of derivatives through history. Leibniz is the one that we still use pretty frequently, and he notates it as the derivative of y with respect to x. Another way that he sometimes wrote it was, let me get this all down. Okay, this one you would say means to take the derivative of the function f of x with respect to x. Okay, so we'll still use this notation especially quite frequently. The other person who was at the very beginning of this notation, it was really between Leibniz and Newton. In fact, they had quite a feud over it, which we'll watch a video on. It's pretty entertaining. Newton, however, did lose the notation battle because he used dot notation, which we just don't use anymore. I think it shows up mostly in a physics context more so than calculus. Instead, we favor Leibniz, and then there's this guy Lagrange. So for this one, we use that f prime of x notation, which can also be written as just y prime. So these two guys made the notation that's still used today most frequently. Sorry, Newton. And just as a clarification for your notes, if we're showing that we're plugging in a value, it's really easy with Lagrange. We would just say like f prime of 2, right? However, with the dy dx notation, it's a little bit harder to show that you've substituted something in. So if we were finding the derivative of y at x equals 2, this one would be notated with this kind of funny bar, and then we would just write whatever the x value is that we're plugging in at the bottom. So this one obviously gets used a little bit more frequently when we're actually substituting in values because it is a little easier to notate. Okay, so now time for some examples. So our instructions say use the definition of the derivative to find f prime of x. Okay, so the function we're going to work with for this first one is f of x equals 3x plus 4. So when we find f prime of x, we're actually getting a function as an answer. So it should have oftentimes a variable still in it, although sometimes it's just a number. And it gives us a function to plug an x value in at, if needed, to find an instantaneous rate of change at that point. So we're going to use our definition of the derivative, which is that limit as h approaches 0 of f of x plus h minus f of x all over h. And we're going to actually use our function given to plug in x plus h. So the limit as h approaches 0, and then we're using that function given, and we're simply plugging in x plus h, and then we're subtracting the actual function f of x, which is just what we started with, the 3x plus 4. Okay, and remember, we can't plug in 0 right now because it's going to give us indeterminate form, especially with that 0 in the denominator. So our goal is to find a way to simplify this so that hopefully we'll be able to do direct substitution. And you will be using a lot of paper for these problems. Just be ready for that, because you do not want to scrunch your work up, because arithmetic errors are the most common sources of frustration with these. Just watch your negative signs and your squaring. Okay, so hopefully things without an h are going to magically cancel out for us. Okay. Oh, look at that. Oh, wait. Oh, Miss Wright. So I'm really glad I actually did this, because this is the very thing that I tell my kids not to do. In this previous step, when we subtract the original function, we're subtracting that whole thing. So we need parentheses around it, because as you just saw when I was canceling these out, I have a plus 4 and a plus 4, which does not cancel out, and then I'm not going to be able to factor an h out of the numerator. What the problem is, as I hope you've already noticed, maybe you were like, no, Miss Wright, what are you doing? Is that this negative sign in this step should have also distributed to the 4, giving us a minus 4. And now I can continue canceling out. And I'm actually just left with 3h over h. That allows me to finally do direct substitution, and the limit as h approaches 0 of 3, that's just 3. Okay, so that means that f prime of x is equal to 3. And one note I want to make here is that the reason we're just getting a constant as the result is because we started with 3x plus 4 as our original function, which is linear. So if we're actually looking at this original function, f of x equals 3x plus 4, okay, you can see that the rate of change here at every single point is the same, because linear functions have a constant rate of change. So this means that our derivative of the function would be a 3, because 3 is the slope, and the slope is constant for all linear functions. So it's not always going to be the case that we're just left with a number at the end. A lot of times it'll look more like an equation because there will be x's left. However, if we're working with a linear function, we'll have a constant rate of change. So for our next example, we're being asked to find the slope of the tangent line of f of x equals x squared plus 1 at the x value x equals negative 4. Okay? So this is asking us to find the derivative. And a lot of times if we're using function notation, f of x equals, we'll stick with Lagrange notation. And then if we have something that simply says y equals right here, then we'll use the Leibniz notation. Okay, so the derivative of the function, limit as h goes to 0, and then there's our definition. Okay, and now we can actually use our x squared plus 1. We're going to use x plus h. Whoa, there we go. Squared plus 1 minus parentheses x squared plus 1 all over h. Okay, so please be careful expanding your binomial in the next step. So that would give us x squared plus 2xh plus h squared plus 1 minus, distribute to our x squared and our 1. Alright, now we can probably cancel a couple things out. And I'm feeling happy right now because everything that I would not have been able to factor an h out of has already canceled out, and I'm left with 2xh and an h squared. So now I can factor out that h to allow me to finally do a direct substitution. Okay, so as h goes to 0, just remember that this is just going to go away, and it's simply going to leave us with 2x. So this is our derivative function. It's like an equation that will give us the slope at any point on our original function, f of x equals x squared plus 1. Now the x value they've specifically asked about is x equals -4. So now that I have this derivative function, I can actually plug that in. So f prime of -4 is going to give me a slope of -8. So that means that instantaneous rate of change, the slope of the curve at x equals -4 is a -8. So then this often leads us to kind of a part 2 of the question. So a common application of the derivative is to then find the entire equation of the tangent line to a curve at a given point. So again, this is the same function we were just looking at, and now that we know that the slope of the curve at -4 is -8, I'm just going to kind of rewrite that here. You can just continue it on your paper. Okay. And we know that that's kind of like the slope. The two things we need to write the equation of any line is a slope and an xy point. So we have the first one, good to go, but we do need a point. And we have the x-coordinate here at -4, but we do not have the y-coordinate yet. So all we would really need to do here is simply plug in into the original function, f of x equals x squared plus 1. We're just going to plug in that -4 here to get the y value. So f of -4 is simply going to be 16 plus 1, which is going to give us a y value of 17. Okay, so if we remember our function notation, we know that's x and that's y, so this gives us the point -4, 17 to work with. So now we have the two things we need, and we can actually write our equation. So I'm going to do all of these in point slope form just because it's fast, and that's all I want. So y minus 17 equals our slope times x plus 4, since it was a -4. And that would be the complete equation of that tangent line to the curve at x equals -4.